Hello friends, in our today's lecture we are going to derive pressure drop equations which we have used in solving numerical of compact heat exchanger. In our previous lecture we have studied some basic concept of fluid mechanics, some basic terms like flux density, mass velocity or mass flux, which we are going to use in this lecture for deriving pressure drop equation. So first, there are two type of compact heat exchanger which is mainly used. First is a plate fin heat exchanger and second is a tube fin heat exchanger. So we are first going to derive pressure drop equation for the plate fin heat exchanger. Suppose we have this kind of geometry. There are two plates from between the flow of any fluid, or liquid or air is flowing. So what happens when any fluid flow from these two plates? Between the gap of these two plates, the fluid sudden introduced to the sudden contraction, it passes through the core of the plate, and again there is a sudden expansion between these two plates. So due to this sudden contraction, expansion, and within the core there is a drop of pressure. Okay, so for if we divide this geometry in a three section, the first section is the entry point at the entrance. The 2 to 3 is a core between the plates and 3 to 4 is an exit between 3 to 4. So first pressure drop happens between this entrance at the entrance point, so that the delta P1 to 2 entrance pressure drop. This is delta P2 to 3 which is a pressure drop at the core, okay, between these two plates when fluid is flowing between the plates, or we can say that in a tube heat exchanger from the tube. Now at 3 to 4 the fluid is going to be face a sudden expansion. So again there is a pressure rise. So delta P 3 to 4, this is a pressure rise. At 1 to 2 pressure drop, at 2 to 3 again pressure drop, and 3 to 4 pressure is going to be rise due to sudden expansion. Okay, so this is the plate type heat exchanger where fluid is flowing between the plates. So now let's understand how pressure drop equation is created. Suppose we have considered this small elementary area, because we know for derivation we have to consider a small elementary area. Then after reaching a standard equation, we are going to integrate and putting the limit to get the final equation. Okay, so suppose we have this small area, elementary area dx, from the total length of the plate, which is capital L. This is plate fin heat exchanger. One flow passage in a plate fin heat exchanger is shown in figure, as we know, with the fluid flow and static pressure distribution along with the flow path, which is shown in this graph. Okay. Now let's understand the incoming flow of the passage is assumed to be uniform. Okay, as it is entrance the passage, it contracts due to free flow area, as we have discussed. Flow separation take place at the entrance, followed by the irreversible free expansion. In the core, the fluid experiences skin friction due to the contact between the plates. So fluid experiences friction, skin friction. It may also experience from the drag at the leading and the trailing edge of an interrupted fin surfaces. It may also experience internal contraction and expansion within the core, as we have discussed in the figure. Now if heating or cooling takes place in core, because due to the conduction from the base wall, the temperature of the fin, or we can say that the temperature of the plate is much higher than the fluid or much lower than the fluid. So at the core there may be a heating or cooling takes place. Due to that heating and cooling in the core, in any heat exchanger, the fluid density, the density of the fluid, either air or water or cooling oil, the density is going to be changed during the flow of the length. So at the core exit, the flow separation takes place followed by an expansion due to the free flow area change. Okay, so at the entry point, the free flow area is going to change due to the contraction. Within the core, due to the heating or cooling, the density of the fluid is going to be changed. At the exit point, again there is a flow area change due to the extraction. So again the expansion takes place at the exit. So then the total pressure drop would be at the entry point within the core, and this is the pressure rise, so that the sign is negative. This is the pressure rise due to the sudden expansion. Okay, so first we find out the core pressure drop, because from the total equation the main pressure drop is due to the core. So first we find out equation for the core, pressure drop for the core. So the pressure drop within the core consists of two contributions. First, due to the fluid friction. First, pressure drop occurs due to the friction, and the second, pressure change due to the momentum rate change. First due to the friction, and second due to the change in momentum. Okay, so within the core there are two reasons for the pressure drop. First, as we can see, this is the friction between the fluid and the plate, and second is a momentum change due to the sudden contraction. Now consider a differential element. This is the differential element dx which we have considered, whose length is dx. Various force and momentum rate in terms of in and out in this element are shown in figure. Okay, this is the figure. This is the small elementary area dx which is shown here. Now applying Newton's second law, we know what is the law is F is equal to ma, mass into acceleration. So in place of acceleration, acceleration is velocity divided by time. So velocity divided by time, this is mass divided by time, it becomes mass flow rate. So m dot, and this is velocity. Again, instead of acceleration, I can write velocity divided by time. So mass divided by time becomes mass flow rate, and this is our velocity, which is supposed to be u maximum. Okay, so F is equal to m dot into u max. So m dot into u max. From our previous lecture, we know that in our previous lecture we have seen in a flux velocity or mass flux that instead of m dot we can write g into area. So this is g into area, and instead of velocity we can write g by rho. From this equation, okay, yes, from this equation we can write m dot is equal to g into area and u is equal to g by rho. So putting value of m dot and velocity, we will get equation, okay, we will get this equation. So it is g square into a divided by rho. So this is the force, g square into a divided by rho. This is the force, or we can say that the change in momentum. So this is g square into a divided by rho at this direction. Okay. Now within this element, within this core, as we have discussed, due to the cooling or due to the heating, the density of the fluid is going to be changed. So this is the entry. At entry it is g square into AO divided by rho. The value of GC is 1, so you can write GC, or instead of GC you can write 1. So g square into AO divided by rho, this is the at entry point. After traveling distance dx, the density is going to be changed. So what would be the change density? So it would be 1 upon rho plus change in density, so that d by dx, change in density due to traveling distance dx. So in a heat transfer subject we have used equation qx plus dx, which is qx plus d by dx of qx into dx, because at that time the heat which enter and travel distance dx, at the exit the heat which enter is qx. After traveling distance dx, it would becomes qx plus dx. Similarly here, at the entry point the density is 1 by rho. After traveling distance dx, the density is going to be changed. So what is the changed value of that density? So it would be 1 upon rho plus d by dx of 1 upon rho into dx. The remaining term will remain same. Okay. Now this is change in momentum. What is the force? So force is pressure into area. So at the entry point, at this point, suppose pressure into area is P into AO. Now change in pressure, the area will remain same. You can see the area is remaining same. So AO is remaining same. The change in pressure. So what is the change in pressure after traveling distance dx? So it would be P, change in pressure. So d by dx of P into dx. Okay. P plus change in pressure, so d by dx of P into dx. Done. Now this tau W, this is a shear stress which is generated due to the wall friction. So this is tau W, which is shear stress due to the wall, into this is perimeter P into dx. So this is stress, this is into perimeter into dx. Perimeter into dx represent the surface, total surface. Perimeter dx is our, this is dx is our length and P is a perimeter. So total area into this is a stress. Okay, done. So this is stress into area which becomes force. Again, done. So now resolving this image, resolving these all forces and momentum, we will get at this first this equation g square into a by gc into rho. Again this is g square into a 1 by rho plus d by dx of 1 by rho into dx. This is positive, this is taken as positive, this is taken as negative. So again this p into AO, this p plus dp by dx into AO, this is again taken as negative due to this direction, minus tau w into p dx. So from right to left direction is taken as negative. So this p plus dp by dx into dx AO is taken as negative. This tau w into p dx is taken as negative. Also this g square a up 1 plus rho plus d by dx 1 upon rho dx is negative, but it is in this side of is equal to, so taken as positive. This is g square a upon gc into rho, and this is p into AO. Okay. Now simplifying this equation, what we need to do here, TW is effective wall stress due to skin friction. P is weighted perimeter. Here this capital P is a weighted perimeter of the fluid flow passages. Now rearranging this equation, this is the complex equation, so we have to simplify this equation. So rearranging this equation, opening this bracket, so g square into a by gc into 1 upon rho. So g square into AO gc, this is rho, will be cancelled out. So after simplifying this equation, after opening the brackets, this is p into AO positive minus this p into AO negative, so it will be cancelled out. The simplifying form of this equation would be minus dp by dx is equal to g square by gc d by dx of 1 upon rho plus tau w p into AO. By just opening the bracket, we will get this simplified equation. Okay. Now defining fanning fraction, which we have just discussed in our previous lecture, that f is equal to 2 tau upon rho v square. Now f is equal to, so simplifying this equation, this 2 is rho v square by 2, we can write this tau upon rho v square by 2. Instead of v, here velocity is u square, maximum velocity um square upon 2, gc is 1. So tau w g square upon 2 gc rho. Using this equation, using this f in this equation, as well as RH is a hydraulic radius, which is AO by P, area divided by perimeter. Also differentiation of this 1 upon rho becomes minus 1 upon rho square d rho. So putting this value of this equation, this and this in above of our equation, we will get this minus dp by dx as it is. Instead of d by 1 upon rho, d by dx of 1 upon rho, we will get minus 1 upon rho v square. So this is minus 1 upon rho v square into d rho, multiplying and dividing by 2. So this is dividing by 2, this is multiplying by 2. Putting value of this, instead of this tau w, we can write f into g square upon 2 gc into rho. So g square upon 2 gc will be common. In bracket, it is 1 upon rho into RH, because instead of AO by P, we can write RH. Okay. So we have this simplified form of the equation. Now this equation is valid for the small elementary area dx. Now we have to derive the equation for the total plate. So we have to integrate this equation and putting the limit. So what is our limit? So limit for the length is x is equal to 0, the total length is L, so x is equal to 0 to L. Limit for the density, so density at inlet is rho I, at the exit, so the outlet is rho O. Pressure is going to change from P2 to P3, so P2 to P3. So integrating this equation and putting the limit. So first, for integration, we have to variable and separable method. We have to use variable and separable method, that we have to separate the dx term and separate the density term. So what we can do, multiply this whole equation, multiply it both sides by dx. So this dx will be cancelled out, so it is minus dp. G square by 2 gc remains the same. Multiplying by dx, so this dx will be cancelled out, so d rho plus f 1 upon RH. Here there will be a dx, because we are multiplying by dx at the both side of is equal to. So this is the simplified form. Now we can integrate So integration, putting integration and opening the bracket. So if we open this bracket, it will become minus integration of g square by 2gc into 2 rho square d rho plus integration g square by 2gc f 1 upon rho rh dx. Now solving this equation by putting limit. So what is the limit for the pressure? So it is P2 to P3. Again here the limit for the density is rho I and rho inlet outlet. Again here limit for the length, which is 0 to L. Okay. So here it becomes upper limit minus lower limit, so that P3 minus P2, but due to this minus it would become P2 minus P3. So that delta P2 to 3, change in pressure or pressure drop at the core, is equal to this minus g square by gc remains as it is. 1 upon rho square becomes minus integration of this 1 upon rho square becomes minus 1 upon rho. And putting the limit in minus 1 upon rho, so that upper limit minus 1 upon rho minus this lower limit. So minus minus becomes plus 1 upon rho I plus g square by 2gc into f 1 upon rh L. Instead of this 1 upon L integration of 0 to L dx by rho, we can write 1 upon rho, which is mean specific volume with respect to flow length. So instead of this term, we can write 1 upon rho mean, so that f, which is mean specific volume with respect to flow length. So replacing this term with 1 upon rho into in suffix m, which represent mean specific volume with respect to flow length. So we have where 1 upon rho mean is equal to 1 by 2 in bracket 1 upon rho I plus 1 upon rho, or Vi plus Vo divided by 2, where V is a specific volume in meter cube per kg. Okay. So we have this simplified form of equation. Now in this equation, further simplifying this equation, this g square by 2gc, take g square by 2gc as common. So what will remain in bracket? In bracket 2, 1 upon rho I minus 1 upon rho O minus 1 upon rho I plus f L by RH 1 upon rho mean. So this is our simplified form of equation. Now in this equation, further simplifying, taking rho I as a common. So in this equation, multiplying by rho I and dividing by rho I. So this is dividing by rho I, in bracket multiplying these two terms with rho I, we will get this rho I minus rho upon rho I into rho I plus rho I f L by RH 1 upon rho mean. So this rho I and rho I will be cancelled out. What will remain in bracket 2 rho I minus rho upon rho, the remaining term will as it is. Now g square upon 2gc rho I as it is. Simplifying further, rho I upon rho minus 1, remaining term as it is. So this is our simplified form, which is delta P23 g square upon 2gc rho I, 2 in bracket rho I upon rho minus 1 plus f L RH rho I 1 upon rho. This is the equation for the pressure drop at the core.